Hello, everyone. All right, so I am double checking my equipment right now, and we are going to be in it in 1 second. So just hang tight for a minute here. Just want to make sure that everything's up and running. All right, and let's see here. I'm not seeing it appear yet in my live chat, so as soon as I see it going, then we'll be good to go. All right, let me try refreshing my screen here again. There we go. So, as you can see, there we go. As you can see, I have a new screen display for the stream, and basically that's just a photo I took just now of my room. So yeah, I really like it, but I don't spend a lot of time in my room. I'm usually outside working all day. So yeah, right now we are gonna be doing 2.3. Now, just to be clear, I'm gonna read through the section first, and then we are going to work through the equations. Conditional statements. Okay, and all right. Let's see here. Write this 2.3. There we go. I don't like that. Sorry, I'm picky. All right, almost done setting up here. It's a little better. Okay, so I'm gonna start reading through this section here. Conditional statements. There is yet another way to combine two statements. Suppose we have in mind a specific integer a. Consider the following statement about a. R. If the integer a is a multiple of 6, then a is divisible by 2. So if a is a if the integer a is a multiple of 6, then a is divisible by 2. That's because 6 is divisible by 2. We immediately spot this as a true statement based on our knowledge of integers and the meanings of the words if and then. If an integer a is a multiple of 6, then a is even, therefore a is divisible by 2. Notice that R is built up from two simpler statements. So let's write some of these out real quick here. Just gonna take the headphones off. I no longer need them. I use them to get going. So first one is gonna be R. If the integer a is a of 6, then a is divisible by 2. Okay. So we're going to say P. The integer a is a multiple of 6. So when we say what is a multiple of 6, that means it's any number that you can divide by 6 and still get a whole number. Okay. So for instance, 30, 5 times 6 is 30. That's a multiple of 6. And that's even, and we know all evens are defined as being divisible by 2, so therefore it's all true. This is starting to get more into the proof stuff. This is more and more what our work is going to look like. Writing sentences and analyzing structure. Finding ways through what we know about mathematics, how to prove that a certain statement or equation is true. But there's going to be still lots of mathematical that we're going to write in terms of there's still going to be a lot of set theory writing. Okay, so we have P, Q, and R. So let's see here. So we have R is if P then Q. That means P implies Q. That's a thing that we haven't covered yet. So I'm going to read here, then we're going to draw the truth table for it. All right, so we have, in general, given any two statements, P and Q whatsoever, we can form the new statement if P then Q. Keep in mind, this is important. The words if and then are very important. If means P, then means Q. So that's important. Keep that in mind. That's going to come up a lot. The words if and then, just like the word not, these are important words. They're key words that we use in mathematics for set or for logic. Anyway, here we go. Now, if P then Q is also written like this. P implies Q. When we assert the statement P implies Q is true, we mean that if P is true, then Q must also be true. In other words, we mean that the condition P being true forces Q to be true. Now, when we do proofs, sometimes we can't easily prove Q. Sometimes it's easier to prove P than to prove Q. Now, proving Q doesn't prove P because P implies Q. So, in other words, Q is a consequence of P, but it doesn't mean that Q would initiate P. In other words, if you take out P, Q may or may not have happened. You understand? But what happens is when we do proofs, and you'll see this eventually, we're going to say, all right, well, we have a hard time proving we have a hard time proving Q, but if we can prove P is real, and if you can prove that P implies Q, then Q is proven. So that's a way how to get around things sometimes. All right. And for example, in this case, so let me just give you an example. So we want to prove that the integer a is even. So let me here. Let me think about this for a minute. Actually, no, that doesn't quite work because here it's proven in Q. Never mind. We'll come to more of these. There'll be lots of these. All right. A statement of the form P implies Q is called conditional statement because it means Q will be true under the condition P is true. Okay, let's do the truth table. If you remember from yesterday, P, Q, P implies Q. Okay. By the way, download the book. It's free. It's part of Creative Commons. I have a physical copy. It's very nice. You could also get it through the link in the description. I don't get anything for it. Just saying support the author. Get the book. It looks very nice on your bookshelf. Just look at my photo. Anyway, also check out my community posts. So if you want to ask something outside of the videos, you can just drop something in community post. So if P is true, Q is true, P implies Q is true. If P is true and Q is false, then this should be false. Let me here. Yeah, true, false, false. Now, if false, we still have two more to solve. Okay, if P is false and Q is true, then now in this case, this is true because all we care about is the Q, right? The P is a way of proving Q. At the end of the day, that's all we care about. We don't care so much about P than as Q because look right here. See, we have this is true, but Q is false. It's still false. On P implies Q, you have to remember our focus is Q. It's not P. So even if P is false, but it implies something truthful, that truth is not tarnished by the falseness that implied it. Again, this is true and false statements in math. This isn't like anything beyond that. So now if P is false and Q is false, now this is very interesting. P is false, Q is false. P implies Q is true. So the way that works is that, in other words, if you start counting, for example, if it's like anything goes. If both statements, if you say apples are grown on the sun, therefore 2 plus 2 equals 5. At that point, anything is true. You see how I did that? I gave you two false statements. Well, if you take something so outrageously false, and then I say, okay, now build out from that. Well, what can you do? You're like, I have this insane statement about apples growing on the sun, which makes no sense. And then I have this other statement saying that 2 plus 2 equals 5. Also doesn't make sense. Both are patently false. So what can I build from that? Well, I can justify anything because I look at it and say, these are two false statements. And if one false statement supplies the other false statement, then anything goes. So that's interesting. Just keep that in mind. That might be useful occasionally. Anyway. So I'm going to read here, continuing after the truth statement, but we're on page 43. Perhaps you are bothered by how P implies Q is true in the last two lines. So here's an example to explain it. Suppose your professor makes this promise. If you pass the final exam, then you pass the course. Your professor is making the promise. You pass the exam implies you pass the course. Under what circumstances did she lie? There are 4 possible scenarios. And it is the same truth table. And basically it says, the first one, T, is you pass the exam. It's true that you pass the course. You pass the exam implies you pass the course is true. You pass the exam, but you fail the last course, it's false. Because it's a contradiction in the sense that you were promised if you pass the exam you would pass the course, but you still were not allowed to pass the course. Therefore, that promise is a false promise. And if you go with, you pass the exam, but you pass the course, it's still true, even though the passing the exam is false, is because you passed the course. Who cares? Who cares how you passed it in this case? In reality, obviously, it matters how you pass. And I myself have taken plenty of F's and W's if I wasn't ready. And I still have them. And this is one of the reasons I'm doing this book, is this is a class I did not pass, and I'm a student, not a teacher, and I'm working to retake this class while I focus on work. Anyway, because work's very important. If you're able to be a successful businessman like myself, I'm a professional landscaper / handyman, work comes first. Anyway, in this case, what you have on the last sentence is you fail to pass the exam, and you also failed to pass the course. So what it's saying is you pass the exam and you pass the course is true because, again, let me just read this out. Let me just read what they're saying here. On the 4th row, you failed the exam and you failed the course. Your professor certainly did not lie to you. That's why it's true. So again, for me, I personally like the idea of just, if you have to build out from one falsehood implying another falsehood, that anything goes. That's mentally how it makes more sense to me. You could say that your professor didn't lie because it's irrelevant, meaning that you met neither of the conditions, not the requirement or the consequence were met. Therefore, the professor didn't lie because you never had to deal with what they said. But again, for me, mentally, I just think of it, okay, you have 2 falsehoods, you could build anything if you're building on foundation of falsehoods, in other words, or an outrageous description where a contradiction. Okay, so for another example, consider this statement. If this month is September, page 44, then there's an equinox this month. An equinox is a day for which there are equal hours of darkness and hours of light. There are 2 equinoxes per year. One in September, the other is in March. And I believe it falls on like the 21st or 22nd, maybe even 23rd sometimes. But yeah, it should be around that time. Essentially, it's the solstice is, what is it, like the 21st or 22nd of December, which is the start of winter, also represents the shortest day of the year. So days actually get longer after that. And the 21st, what is it, June? So that is going to be the longest day of the year. and after that, days get shorter. But because of the the summer still gets warmer, even though technically because of the run up. What happens is it's just accumulation of warm days, and the same thing in winter. It starts to get cold, even though technically the sun's starting to come closer to the how should I describe this? The Earth starts to get closer to the sun. I don't remember the exact structure of how it works. I'm not an astronomer. Don't quote me on this. I'm sure I got plenty wrong. But I know about solstices and equinoxes because I pay attention to that stuff as a landscaper. Anyway, I need to know what time the sun is down for work. Anyway, continuing on here. So let's see here. This is more P implies Q. All right, so I'm not going to go through necessarily every example, but it's the same kind of P implies Q. All right. Just going to read on. As P implies Q is a true statement, in mathematics, whenever we encounter the construction of if P then Q, it means exactly what the truth table for implies expresses. That's what I was saying. If you see if P then Q, remember P, we can go like this, parenthesis. This is going to be our statements. Then this is going to be P implies Q. Okay, just remember that. So in other ways, there's a list of them, and these are important ways to remember how they could appear. Okay, if P then Q, okay, Q if P. So we could say you will graduate only if you pass the final exam. Or you will graduate if you pass the final exam. So we give the consequence, and then we give the way that what would determine that, the determinant. Q whenever P. You get a good letter grade whenever you graduate or something. I don't know. Q provided that P. You pass provided that you get a passing mark in your final. Whenever P, then also Q. Whenever you get good grades on your final, then you also pass. P is sufficient condition for Q. This is an old one. That's how they used to write it in old math books, but we don't use it as much, I guess. But I'm not a mathematician, all right? I'm a landscaper, so don't quote me on that. So P is a sufficient condition for Q is basically the way you would do that. And by the way, a lot of my knowledge is just, I'm just reciting things that I remember from math class from my teachers. So it's just like, like I'm not even coming up with a lot of like examples and whatnot. A lot of it's just like, oh, hey, this is I absorbed through paying attention in class. Anyway, P is a sufficient condition for Q. Okay. Getting a high mark in class is a sufficient condition for graduation. Okay. Q, it is sufficient that P, this is a little tricky. For Q to graduate, it is sufficient that you get a high mark on your final. Q is a necessary condition for P. So Q is a necessary condition for P. This is for me, I have to mentally wrap my mind around this one. So for Q is a necessary condition so graduation is a necessary condition for getting a high mark. It doesn't mentally wrap all that well, but just roll with it. And then for P, it is necessary that Q. So this is another one you got to mentally kind of wrap yourself. To get a high mark, it is necessary that you also graduate. Again, this is where I start to cringe up a little bit, but trust me, this stuff is based in fact. And by the way, in case you don't know, based is opposite of cringe, which me explaining that is kind of cringy. Anyway, P only if Q. P only if Q is you get a high mark only if you graduate. Yeah, just roll with it. Just trust me. It's hard to wrap your mind around it. Just roll with it. Okay. So these can all be used in the place of and mean exactly the same thing as if P then Q. So just you got to memorize these lines and then memorize the structures. Like when you read a sentence, you try to see which one of these maps. Where is the P? Where is the Q? Okay. You should analyze the meaning of each one and convince yourself this captures the meaning of P implies Q. There you go, that brain melty stuff. You have to convince yourself. Even if it feels a little cringy, you have to just, kind of squint your eyes and say, yes, it'll work. And, even if it doesn't make sense at first, if the math book tells you, hey, this is how it's done, you just got to trust it. Now, just like there are occasionally misprints and whatnot, like in yesterday's stream, we did algebra and trigonometry. I found a misprint, which was very obvious. We were doing question 45 and question 44. It was exactly the same setup, meaning that we were dealing with scientific notation, very basic stuff. But essentially, the size of it, the scientific notation, whoever was copying it, they copied the dimensions directly from the previous question. So but the answer was written differently. The answer was written in a way that made sense in terms of like real world application, the size that we were talking about in scientific. So long story short, I was able to demonstrate conclusively why that was a misprint. But don't assume that if you don't understand something, it's a misprint. Usually you just don't understand something, okay? If you can absolutely conclusively prove something and demonstrate how a misprint could have happened and why this is exactly a misprint, then that's when you know. But again, they're rare, and it's like maybe 1 in 1,000 questions is going to be a misprint. So it's just like that. Anyway, so continuing on, let's see here. Then these all can be used in place of mean exactly the same thing as if P then Q. You should analyze the meaning of each one. Convince yourself that it captures the meaning of P implies Q. For example, P implies Q means the condition of P being true enough, sufficient, to make Q true. Hence, P is a sufficient condition for Q. The wording can be tricky. An everyday situation may help clarify it. For example, consider your professor's promise, you pass the exam, you pass the course. This means that your passing the exam is sufficient, though perhaps not necessary, condition for you passing the course. Thus, your professor might just as well have phrased or promised in one of the following ways. Passing the exam is a sufficient condition for passing the course. So we look back at our list. P is a sufficient condition. So we're going to say P means passing the exam is a sufficient condition for Q passing the course. Okay? For you to pass the course, it is sufficient that you pass the exam. So we go back. For Q, it is sufficient that P. So for you to pass the course, for you to graduate, it is sufficient that you get a good grade in your final courses, for example. However, when we want to say if P then Q in everyday conversation, we don't normally express this as a Q is a necessary condition for P, or P only if Q. Such constructions are not uncommon in mathematics. To understand why they make sense, notice that P implies Q being true means that it's impossible that Q is true, or P is true, but Q is false. Meaning that if P is true and P implies Q, therefore Q has to be true. You see how that works? If we can establish that P implies Q, and if we can establish that P is true, then Q cannot be false. So in order for P to be true, it is necessary that Q is true. Hence, Q is a necessary condition for P, and that means that P can only be true if Q is true. So let's roll that back a little bit. Okay, so we've established, pretty straightforward, P implies Q, and if P is true, so I'm just going to start drawing this a little bit. So this is what, let's just say we established this. P implies Q, right? Okay. And then we're going to say, well, if P is true and P implies Q, therefore true implies true, therefore Q has to be true. Okay, that makes sense. Now, next part. So, yeah, so in order for P to be true, it is necessary that Q to be true. So, in this case, in order for, we have to establish P implies Q again. And if we say, if we can establish this part, this relationship exists, then what happens is, if Q is true, look where the truth is, here and here, then P has to be, a minute here, that's not right. Hang on a minute. I'm sorry. Okay, it's not essential. Here, let's put this one more time. Let me read this one more time. Again, I'm studying this as I'm doing this, so I do have these hang-ups, and need to go back and understand what I'm saying here. Okay, so in order for P to be true, it is necessary that Q is true. In order for P to be true, so we have true, true. It is necessary that Q is true. Hence, Q is a necessary condition for P. It's getting back to this. Now, again, that's just like a mind melter, one of those ones. It's hard to really just, when you start writing math and the mathematical relationships are a little easier than just language constructions in ways that we're not used to doing. And that means P can only be true if Q is true. So just remember, P only if Q. So again, this is like a several step process. It's very hard right now to just kind of like break it down in ways that just don't sound like mush. So we're just going to not worry about that and simply remember the formula. Remember all of those relationship formulas on 44. If P then Q, Q if P, Q whenever P, Q provided that P, whenever P then also Q, P is a sufficient condition for Q. For Q, it is sufficient that P, Q is necessary condition for P. For P, it is necessary that Q, P only if Q, okay? You got to remember that. If you can remember that, you're going to be good. All right, let's do some stuff. Right. Okay, let's turn off this layer. Actually, I'm just going to go like this. Okay, and okay, still kind of working out how to do this pen stuff properly, but getting there. Okay, so let's just use this as a base. I'm gonna start another one. There we go. Okay. Question 1. I'm gonna write it first. Oh, it's linear algebra. We'll be getting to that. I got 6 books planned right now, getting courses that of these 6, I've only passed 2, which is Calculus 1 and 2. I have linear algebra, Calculus 3, and well, actually, I'm sorry, I've passed trigonometry and algebra, so technically 3 of the 6 I've passed. But the other 3 I need, and the 3 that I passed, I just need to do them better. Okay, sorry, my voice gets a little gravelly around 11. Okay, so a matrix is invertible provided. Okay. So if I remember correctly, if you have linear algebra, and if you determinant means that it's like a multiplier of it. It's like, oh, like think of it like a base thing. But it, again, you have matrices. Anyway, I don't want to get into it too much, but basically, this is something that we'll be covering in linear algebra when I get to that. It's pretty fun. A matrix is invertible provided that its determinant is not zero. So we look for the word provided or necessary condition. A matrix is invertible. Okay, we can say Q is a necessary condition for P, I suppose. Provided, let's see here, the determinant is not zero. So in this case, we have to decide what's P, what's Q. Let me see here. A matrix is invertible provided that its determinant is not zero. If P, its determinant is not zero, then a matrix is not invertible. So we're going to say, so write the sentence, changing it. So we have to write okay, so we're going to say which is P, which is Q. A matrix is invertible. This is Q. Okay, and then we're going to say its determinant is not zero. That's P. Okay, and because its determinant is not zero, a matrix is invertible. Okay, the condition that makes the result, the condition is its determinant is not zero. So let's use the words if a matrix's determinant is not zero, then the matrix is invertible. Okay, that's how I see it. If a matrix, that's not how you spell matrices. I gotta look this up. No, it's matrices. I'm trying to see how matrices. I'm looking for the proper way to spell it. Okay, this isn't what I want. Okay, doesn't matter. Just I'm gonna roll with that. If the matrix's determinant is not zero, then the matrix is invertible. Okay, well, let's take a look, see what the book says. All right. We are in 2.3. If a matrix has a determinant not equal to zero, then it is invertible. Yeah, okay, book agrees. That's good. All right, next. For a function to be continuous, it is necessary that it is integratable. Okay? 3. For a function to be continuous, this is an easy one, very easy. Okay, but before I explain why this is easy, let's actually just try to establish P on our own. So we have a condition, a result, a function to be continuous. Well, and then that's Q. So this is Q. It is, this is P. Okay. The fact that it is integratable, it means it's continuous. This is referring to the fundamental theorem of calculus. So basically, if a function is continuous, it's integratable. If a function is integratable, it is continuous. Well, actually, not necessarily. I got it backwards. But basically, this relates to the fundamental theorem of calculus. And now you can see why I say I'm going to be doing all the books, right? It's because there's large gaps in my knowledge, and math is one of my 2 degrees that I'm pursuing. I only have an associate's degree right now in computer science. I'm pursuing a double bachelor of computer science and pure math at West Chester University. So that's why, to fill in the gaps. So, but why is it easy though? Well, let's look at our list. It is necessary. Find the ones with Q is a necessary condition for P. No, wait a minute here. It's necessary. It is necessary that for P, it is necessary that Q. Actually, I got this wrong. I haven't checked the answer yet, but I'm looking for P. It is necessary that Q. It is necessary that Q. This is not how it should be. So this is why it's easy, and I found my mistake too. Great. Granted, it's not a mistake, so I turn it in and check the answer here. So let's find out what that comes out to. For P, function to be continuous, necessary that it is integratable. For P, it is necessary that Q. Okay, although, let me think about this for a minute here. That's the structure. Okay. Let's see here. Or we can say, let's think about this for a minute. Q is a necessary condition for P. Let's see here. For a function to be continuous, let's try to write this as P and Q. P implies Q. If a function is continuous, then it is integratable. If a function is integratable, then it is continuous. That's wrong. If a function is integratable, then it's not necessarily continuous, though, because you could have ranges. You could have a range of where you can or can't integrate it. I would say it's like this. Yeah. If a function is continuous, okay, that's how I think it is. Okay, let's take a look. Okay, we have 2.3. If a function is continuous, then it is integratable. Word for word. Perfect. So yeah, look at the list, memorize the list, okay? Very important. Okay. Okay. An integer is divisible by 8 only if it is divisible by 4. That makes sense. Well, what if it was the other way around? An integer is only divisible by 4 if it was divisible by 8. That doesn't make sense. Wait a minute. Hold on. I'm confusing myself. That's part of proofs, by the way. That's normal. Okay. So let's just use example. Let's say 32. And that's divisible by 8, which is actually 4. So, probably a bad example. Let's just try one that doesn't give us 4. We're going to say, okay. Okay, let's say that. An integer is divisible by 8 only if it is divisible by 4. So what is the necessary condition? In this case, this integer is divisible by 8, but it's not divisible by 4. Well, I mean, it is technically. You could 8 times 10. Sorry, 4 times 10. But it is also divisible by 8. They don't give the same result. Okay, I'm confusing myself. Okay, let's look at it. What has to be the leading rule here? What is the more restrictive rule? So we're going to look at, let's see here. Only if it is divisible by 4. If it is divisible by 4, then it is divisible by 8. No. If it is divisible by 8, then it is guaranteed to be divisible by 4. Yes. Okay. This is P. This is Q. If you can divide it by 8, guaranteed you can divide it by 4. But if you can divide it by 4, you're not guaranteed to divide it by 8, like 4. So, for example, if you can divide 4 by 4, that gives you 1. Whole numbers, when we say we could divide it by it, we're not talking about fractions here. So, what we have to do is, and this is kind of, you can work that. I thought about it, how to solve this. Again, the other way to do it is look at the rules. P, let's see here. Last one. I'm gonna write the rule. Can't spell. Okay, that's the last on our list there. And the list is on page 44. So just go there, memorize it. Very important rules. P only if Q. Only if. Only if. That's it. No more work necessary. You find an only if, your P, your Q. I was able to demonstrate it by saying, if you can divide it by 8, guarantee you can divide it by 4, but not vice versa. So I just went the extra mile to prove the point, but that's how you do it. You remember the rules and just pull them out. Now, if P then Q. Now we have to write it as if P then Q. If then okay, let's read it. First, we have our statement in the form of P only if Q, the original. An integer is divisible by 8 only if it is divisible by 4. And now we have rewritten it as if P then Q. If, taking the P, an integer is divisible by 8, then it is divisible by 4. Cool. And we can stretch this, I suppose. All right, let's check the results, see if the book agrees or not. But that was a pretty strong argument. I'm feeling pretty good about this one. 5. Word for word. Book agrees. All right. Let's see here. 7. Okay. Which is P, which is Q. A series converges whenever it converges absolutely. Well, let's look at the rules. Well, I'm liking whenever P, then also Q. Or, wait a minute. No. Hold on. We needed the words then also. Q whenever P. I'm calling this, see here, calling this Q. Q. Whenever. Show you what's P. Okay, that's how I call it. Now rewriting it. Now we're not going to write it converges absolutely. If it converges absolutely, then a series converges. Where I'm going to, the it and the series, you can flip the names around, obviously. I mean, in other words, you start it by writing the sentence, make it intelligible. So instead of writing it, I'm just going to say a series for P. If a series and if you don't understand what any of the series convergence is, it's infinite sets. It's like you have like you take 1/2 plus a quarter plus an eighth plus a 16th plus a 30, and you find out you keep adding those half of the previous one, and where does that lead to? Where does that converge to, basically? It's 1 plus a half plus a quarter. I believe it converges to 2, if I'm not mistaken correctly. That specific series. But the whole thing is that there's P series and there's all. We'll get to that. It's calculus 1 and 2. If a series converges, if a series converges, absolutely, full of P. The it becomes a series, if a series. The if is from before. A series replaces it, converges, absolutely.
Okay, I found this on the web for replaces it converges absolutely.
What?
Check it out.
Siri, I wasn't talking to you, but thank you anyway. That's funny. Hey, Siri, say hi to the chat.
To who?
Say hi to the chat.
To who?
Never mind. Okay.
I won't send it.
Okay. That was hilarious. I was talking about series, and Siri picked it up as Siri instead of series. That was funny. If a series converges absolutely, if, we're going to do if P then Q. If a series converges absolutely, then it converges, which kind of makes sense. If it can absolutely converge, then it does converge. Then it converges. If a series converges absolutely, then it converges. Okay, let's check that. 7. If a series converges absolutely, then it converges. Word for word. All right, that's good. And the reason I'm able to get these word for word is because they're written in a way that if you just line it up with whichever one of the forms on page 44, if P then Q, Q if P, Q whenever P, Q provided that P, whenever P then also Q, P is a sufficient condition for Q it is sufficient that P, Q is a necessary condition for P it is necessary that Q, P only if Q. They're all P implies Q. Just remember those. Okay, 9. Here we go. Notice that it didn't say you have to understand the sentence. You just have to understand English, and then you just recognize the pattern. You find the form of the examples or the structures on page 44. You don't have to fully understand what the sentence means. You just have to understand the structure for our purposes right now. It certainly helps, like knowing about like what can divide what and so forth, convergence, divergence, and whatnot. These things are important, but at this point you can solve this even if you didn't know that. Okay, a function is integratable provided the function is continuous. So what form can we use? Q provided that P, well, that probably is it. Okay. So I'm thinking this is going to be Q provided Q P. All right, let's write that. If P then Q now the form. If a function is continuous, P, then it is integratable. Integratable. Okay. Okay, so that's of the form if P then Q. All right, let's double check the work. A function is integratable provided that the function is continuous. They didn't use provided that, but provided here in the structure of it lends me to believe that's what they're going for. And not only that, and we could have easily fit that in there, and it still makes sense in the form of English. It's fine. As an English sentence, it would totally work. Then we rewrite it after we've established which is P, which is Q, in the form of if P then Q. If a function is continuous, then it is integratable. Okay, so 9. Yep, and that's what they wrote, except they said, then that function is integratable. I wrote it, which is fine. In this case, it refers back to the function that is continuous. So that's fine. Same answer. 11. You fail only if you stop writing. Ray Bradbury. You know, that's true, but a lot of dude bros love to use that concept to keep people to keep doing things that mathematically don't make a lot of sense. You know, all the hustle culture that's infesting YouTube and all that crypto shenanigans. When you look at it mathematically, it's just, I mean, if you want to play it like the lottery, sure, you know, play it like the lottery, whatever, but please don't put your life savings into that kind of stuff. You know, don't YOLO your life savings on anything. Don't drop ship your life savings into drop shipping. You fail only if you stop writing. Ray Bradbury. Fahrenheit 451. There's a wild scene in it where I believe this is in the play version of it, where the main protagonist is talking to the antagonist, and I forget their names now, but long story short, the guy shows him to his collection of books, which in their world, it's illegal to have books. They all get burned. The firemen burn books. They don't save houses. They burn books. Anyway, so what happens is, and he asked him how can he have this whole collection of these books when books are outlawed, and he shows to him all the dust covering them, and he says, well, they're not in use, so they're not books as a function. They're simply, you know, standing blocks of very thin paper that no one ever uses as a book. So it was an interesting point. It is a, but anyway, Fahrenheit 451. Go and read it. It's in the vein of 1984. Same vibes. Okay. If you fail only if you stop writing. Okay, so then we need, see here, let's look at the form. P only if Q. Perfect. So hang on. That doesn't make sense though. Let's rewrite that. If you fail, okay, if P then Q. That wouldn't make sense. If you fail, comma, then you stop writing. It doesn't make sense. I would say this is let's try it as Q if P. If you stop writing, you fail. That makes more sense. Or we could say only if you stop writing, you fail. No, we're using if the form. If you stop writing, you fail. The only gets dropped. We simply rewrite as if P then Q. So the you know, if you look at it, the only if, you could say P only if Q, but then it would be, if we say P only if Q, if this is P only if this is Q, and let's say P implies Q, so then we're going to say if you fail, then you stop writing. If you fail, then you stop writing. That loses the feel of the original sentence, right? You can see that. It kind of inverts the message. So I would say this is the form Q if P. If we say this, if P. So we're going to say Q if P. And if you rewrite this, if P then Q, if you stop. Okay. If you stop writing, then you fail. You fail only if you stop writing. So failure is a consequence of stopping writing. The thing that determines of success or failure, the determinant is P here. So yeah, If you stop writing, then you fail. If P, then Q. That's what I'm feeling for. Oh, okay. Yeah, I should have been more rigid. I should have stuck to, if they have that form, you absolutely have to take it. So, no, the where I didn't get it right is how they restructured it. If you fail, then you have stopped writing. So they changed the stop to stopped in a past tense. So that makes sense. I wasn't thinking in those terms. A limit of imagination on my part, but let's fix that. You learn from your mistakes. Okay. Let's try this. That's why I was uncertain about it. I was like, yeah, if you look at the book, stick to the form. If you see the form, you modify the past tense, present tense of the verb, and then that'll be it. Okay, so we're gonna say you fail, and only if. So we're using the P only if Q. So we're gonna say if you fail. Now, remember, this is the English language. It can be a little wonky and we have to change the tense. But in math, it's a little different. You know, we don't have to worry so much about past and present tense. So whenever we're doing this, not as English writers, but as aspiring mathematicians. Then you have stopped writing. Okay. All right, and last question, 13. Whenever people agree with me, I feel I must be wrong. Oscar Wilde. Okay, Oscar Wilde, The Picture of Dorian Gray. Go read it. It's a good book. So yeah, a guy falls in love with his own image. Guilty. But anyway, he has a painting done, and basically he doesn't age, but all his sins and misdeeds are shown on the portrait, and it slowly becomes hideous due to his degeneracy, and spending time on the internet. But read the book. It's a good book. I love how they're using, instead of just like random structured sentences, they're using quotes by great writers. I really appreciate that about the author of this book. You go to clearly this is a well-read person who, instead of, or perhaps, it could be that they, obviously, when a person writes a book of this density, they probably have graduate students assisting with it. I don't know. Maybe they didn't. But I would imagine that's how they would do it. And whoever did it for these examples clearly is well read. Because when you're putting together something this dense, you're not going to drag your feet. You have to be able to just pull it right out of your hat, so to speak. And just know on the spot instead of or otherwise you just restructure a basic sentence in a way and just move on to the next part, in the next part. Because the book's just only getting started. You can learn a lot by looking at the structure of things, the type of examples people use and whatnot. Okay. Whenever, looks like this is whenever P then Q, I guess. Q whenever P. Oh, hang on. There's two whenevers. Q whenever P and whenever P then also Q. But we don't have a then also. Whenever people agree with me, I feel I must be wrong. We're going to say Q. Whenever people agree with me is Q. This is Q. Let's see here. I feel I must be wrong. P. Actually, let's take out the whenever. Just so that... Q. Okay. I don't have much room to write this. It's going to look unintelligible, basically, after I finish this last part. Hold on. Let's see if I can move things around a little bit. Give myself... No, can't give myself any more room. Maybe I can move things around a little bit. No, it'll be a big mess. Okay, I'll just have to squeeze it in here. Whenever people agree with me, I feel I must be wrong. And we're going to say, if people agree with me... No, if P... Whenever people agree with me, I feel I must be wrong. If P then... Oh, P implies Q in the form of if P then Q. If I feel I must be wrong, then people agree with me. If I feel I must be wrong, then people agree with me. Yeah, I guess it kind of maintains the original structure. Close enough, as long as we get the alignment right. I'm gonna try to... I really do need room here. Okay. Let's see here. I'm gonna try to drop this down here. Okay. I think I just provided myself just enough room to do this. Okay. We're gonna say, whenever I feel I must be wrong. So if P then Q. If I feel I must be wrong, then people agree with me. Okay? All right. Let's see. If people agree with me, then I feel I must be wrong. So whenever people agree with me, I feel I must be wrong. So I got this one wrong. So whenever people agree with me, I feel I must be wrong. I went with Q whenever P. And they went with P then Q. Yeah, people agree with me. Okay. They must have gone with, I said, whenever. Oh, that's what it is. That's why I screwed up. Whenever people agree with me. So it should be Q whenever P, not whenever Q then P. That alignment's important. There is a whenever P then also Q. That's where I screwed up. You see, that's it. If the whenever comes first, you have to be, it's a P then. If the whenever is between the two, between the cause and the effect, then it's Q whenever P. So in other words, effect whenever cause. So that's where I made a mistake, and it's good that I caught it that way, because otherwise you want like, well, they're both whenevers. How do you know which one to go with? Go with the outer one. Whenever P, then also Q. Okay, let's fix that. You learn just as much, if not, actually, you learn a lot more from your mistakes, because you're forced to, I mean, it sinks in more permanently, I would say. So, and in a sense, we are designed for learning from our mistakes, because in the wild, if you don't learn from your mistakes, you might not get a second chance to learn from that mistake. If you just keep making the same mistakes over and over. So yeah, mistakes are a great way to learn. Don't ever feel bad if you make a mistake. Don't ever feel bad if you fail. It's just another opportunity to bounce back and get better. Analyze what you do something different. Just don't repeat the same mistakes over and over and over. Okay. If I feel, so we're doing if P then Q. If I feel, and that's, yeah. Wait a minute here. No. Speaking of repeating the same mistake, at least I caught it. So we're going with Q whenever P. No, I'm sorry. I'm confusing myself. Whenever P, then also Q. So whenever P, whenever I feel I must be wrong, then also people agree with me. Whenever now, we're not going to use the also. We're just going to say, because that's the form. So basically, we're using the whenever P, then also Q. But it can be whenever P, then Q. But it doesn't matter. It's basically whenever the effect, whenever cause, then effect. Because the whenever is on the outside and not between them. The cause in this case is I feel I must be wrong. And that's P. Wait a minute here. No. Oh, okay. That's what's confusing me. I didn't correct it up here. Okay, well, I haven't resubmitted it yet, so I resubmit them and recheck my answer. Whenever people agree with me, whenever is P, so this is P. That's why I keep repeating that same mistake. But hey, I'm learning. Now at least I caught it midway a couple of times. That's the problem. I erased the sentence, but I didn't change it up top. Is what I should have done. Because that's where I keep making the mistake from. That's where it needs to be corrected first, so I could write the sentence correctly. We're taking the, let me write over here. We're going to use, Okay. P, Q. Whenever people agree with me. So instead of whenever, now we flip it to the if P then Q form. If people agree with me, comma, that's P, Q, then I feel I must be wrong. Okay, if people agree with me, then I feel I must be wrong. If P, then Q. All right, let's check that. I'm rechecking, obviously. Okay, if people agree with me, then I feel I must be wrong. Good, okay. So again, I was rechecking knowing that I already messed it up once, but I was able to recheck it and do it correctly because after understanding that the whenever is on the outside, it means whenever cause, then also effect. If the whenever is between, then it's then it's cause. Sorry, let me rephrase that. Start from the top. If you have the word whenever on the outside, then it's going to be whenever cause, then also effect. If the whenever is between cause and effect, it's going to be effect whenever cause. Just remember that. One more time. All together now. If the word whenever comes before you hear about the cause or effect, the structure is going to be whenever cause, then also effect. If the word is between cause and effect, the word whenever, then it's going to be effect whenever cause. Remember that. Okay? All right. That's it for this stream. And I will see you guys tomorrow. Thank you for coming.